So thank you very much. And I'm going to break the symmetry and use this screen just for a change. So, so I would like to tell you a little story about how to change quantum statistics or to convert quantum statistics into energy. And this is work done in collaboration with the theory group of Thomas Busch in Okinawa and the group of Arthur Videra in Kaiserslautern. That's the group where the experiment I'm going to present was actually performed. So let me start with something I guess we all agree on, namely that thermodynamics is the science of energy conversion, and there are many forms of energy. We have thermal energy, mechanical energy, chemical, elastic, electromagnetic, whatever you wish to have at this place. And since the very beginning of thermodynamics, heat engines that convert thermal energy into mechanical work, that is motion, have played a prominent role. What we see down here is the heat engine of James Watt, 1783, so that's 240 years ago. And down there, a modern car engine, and they all convert heat into work. So now in the last few years, heat engines have been successfully downscaled down to the nanoscale, a few systems consist of a few atoms. If they're very small and very cold, we enter a regime where quantum mechanics dominates the dynamics, so we enter quantum-dominated heat engines. And here are just a few examples. What we see here is maybe one of the first experimental realizations of a quantum heat engine in the quantum regime using NV centers. The one here in the group of Roberto Serra was done using NMR, down there cold atoms. But at the end of the day, all these engines, even though they run in the quantum regime, they're dominated by quantum dynamics, they still convert heat into work like classical engines. And the question one might ask is there a generally quantum energy conversion mechanism? And that's actually the topic of this talk. And in order to answer this question, let me start by introducing the mean energy of the system, which is defined, so that's some elementary quantum thermodynamics, which is nothing but the expectation value of the Hamiltonian of the system. Now let's assume we make a small change, small variation. Then this change of energy can be split in two contributions. The first one is usually called work. The second one is usually called heat. The work part is connected to a change of the Hamiltonian. So this is typically what happens if you change some external parameter of the system, you drive it externally, while the heat is related to a change of the state, a change of the population. And now let's have a look at this formula down here, which you all know very well. That's the occupation probability for fermions and bosons. And if you want to change that occupation probability, you have three different ways of doing that. Conventionally, people would tell you, well, I can change it by changing the temperature, or the inverse temperature better. At the same time, we can also change the chemical potential. But now let's assume just for a second that we can change the sign down here, meaning we change the statistics. And in principle, mathematically, it should be possible. Let's talk about physics. Brief reminder, there's a big difference between bosons and fermions. Bosons have a symmetric wave function and have an integer spin, whereas for fermions, the wave function is antisymmetric and they have half integer spins. Fine. The interesting property here is that fermions obey the Pauli exclusion principle, and this can be stated in a very simple way. Two fermions cannot occupy the same state. So it's a very simple observation, but it has deep physical consequences. It explains, for instance, a great variety of phenomena. If you look at atomic physics, the electron shell structure in atoms is directly linked to the exclusion principle. The stability of condensed matter, the very fact that you can sit on a chair without going through it is due to Pauli. And even if you go to astrophysics, the existence of white dwarfs or even neutron stars is a physical consequence of this exclusion principle. So now if you consider a system of bosons or fermions and you put them in a harmonic trap, go down to zero temperature, two different things are going to happen. The bosons, on the one hand, are all going to collect in the ground state, whereas fermions, because of the exclusion principle, are going to be stacked. Physically, this means that even though you are zero temperature, the pressure of a Fermi gas is not going to be zero, so it's going to be a non-zero Fermi, or some people call that the degeneracy pressure. At the same time, there's going to be a Fermi energy down here, which is also different from 0. And just have a look at the corresponding Fermi temperature, which is defined down here. This can be actually very, 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 very large. So for metals, for instance, if you remember your solid state physics lectures, it's about 10 to the 5 Kelvin, which is much larger than the temperature of a normal heat reservoir. And actually, if you take copper, the Fermi temperature is of the order of 80,000 Kelvin. And if you compare that with the temperature of at the surface of the sun, it's only 6,000 Kelvin. So it's more than a factor 10 more, right? So in a metal, the Fermi temperature is actually much, much, much higher than the temperature at the surface of the sun. Just think about that for a second before I continue on. The second is over. So now if you compare the total energy of a system of fermions in this state and a system of bosons all down here, you're going to have an energy difference, which some people call de Pauli energy, and these can be huge as well. So if you again consider the case of an ideal gas, no interactions, trapped in a harmonic potential, you realize that this Pauli energy scales like the number of particles squared. So if you take something, a gas of 10 to the 5, 10 to the 6 particles, you square it. This is a huge amount of energy. Now the question is, how do we actually change the statistics, right? So mathematically, it's very easy. I replace a plus by a minus or a minus by a plus, right? That's very easy. How do you do it now in the experiment? But the answer is not that complicated. Even though the spin is an intrinsic quantity of a particle, if you now take two fermions, put them together, this gives you a boson. So that's the physics of pairing, if you wish, pairing phenomena. And in a concrete experimentals, in concrete systems, this is directly linked to what people call BCS-PEC crossover, namely the crossover between the Baden-Cofer-Schrieffer theory of superconductivity on the one hand and the theory of Bose-Einstein condensation on the other. So what happens in such a transition or such a crossover can be seen here in this picture. It's basically a transition between weakly coupled individual fermions, like these two, to strongly coupled bosonic pairs, bosonic molecules, and this is done by changing the length scale of the pairing. In other words, by changing the size or the distance between two atoms in such a pair. So by doing that, you can actually move from fermions to bosons. So this is actually a generic feature of interacting Fermi gases. This holds true for superconductors, this holds true for excitons in semiconductors, this holds true for neutron stars. Experimentally, it's much easier. Well, the first experimental observations of such a crossover has been done in cold atom systems, dilute cold atoms. And this is done by varying the scattering length using so-called Feshbach resonances. So basically, you play with the Zeeman effect by applying some magnetic field. So what you see down here is the bosonic side, where the scattering length A is positive, so that's the BEC side. On the other side, down on the left-hand side, you have the fermionic side, where the scattering length is negative, so that's the BCS side. And what I'm going to focus on this talk is what we see down here. So here we have a bound state, we have some bosonic molecules, and we're going to move up here until this point where Fermi statistics occurs, and some people call that the unitary limit. That's just a transition where you don't have any bound states anymore, and where the scattering length actually diverges. And it's interesting for other reasons, because everything becomes universal. You have all the details of the system actually disappear. So how do we do that to cyclically convert quantum statistics into work? So I'm going to go back to my first slide. I'm going to talk about heat engines. So if you remember the normal car engine, the normal auto engine, the cycle consists of 4 different steps. You have first a compression step, where you perform some work, W1. Then you have a heating phase, where you exchange heat with a reservoir. Then you have an expansion phase, where you perform some work, W3. And then you cool down to the initial state. So that's a normal heat engine cycle. What I'm going to do now is I'm going to replace this heating step by some fermionizations. I'm going to change statistics from bosons to fermions, and here I'm going to replace the cooling part by a bosonization step. What happens in the system is depicted here on the side. So I start with the BEC. I perform work on it, I compress it by changing the frequency of the trapping potential. Then I'm going to fermionize it. I'm going to change the statistics. So I'm going to go from the BEC to a gas of fermions. I'm going to have this Fermi energy. I'm going to have this Pauli energy exchange. And then I close the cycle by expanding it, by changing the frequency again, and then I go down to my initial state by bosonizing it one more time by bosonizing it. So that's a sketch of the heat engine cycle. What you see on the right-hand side is actually the measured cycle that was implemented in the experiment. So it's a PV diagram like what we teach students in thermodynamics. It's not an ideal gas, it's not a classical ideal gas. So what we have here, this red line is actually the equation of state of the BEC. The blue line here is the equation state of the Fermi gas. Let's start at point A, which corresponds to this one. So we start compress by increasing the pressure. Then we fermionize it. And if you remember that the Fermi gas has a much higher pressure than the corresponding bosonic gas, we expect some increase in pressure, which happens here. And then you expand, you go down, and then you bosonize again, and you close the cycle. And then you can repeat this as many times as you wish, in principle. So at the end of the day, in this cycle, it's a Boring Otto cycle, or heat engine cycle, where the heat exchange is replaced by a change of this Pauli energy, which is due to the Fermi statistics, to the Pauli exclusion principle at the end of the day. So that's one slide presenting the system. It's an ultra-cold gas of lithium atoms, if you're interested in some details, in a harmonic trap. So that's the cloud, the cigar shape. And the only thing which is really measured is the size of the cloud using some absorption imaging techniques. So by looking at this picture, you can get the size of the cloud. By looking at the density, you can get the atom number. And that's actually the only thing you really need to do thermodynamics, because you have a gas in a harmonic potential. So if you have the number of particles, and if you have the width in all three directions, you can actually easily determine the energy, the mean energy. And that's really the only thing that is really measured in the experiment. And then they will measure all different things to make sure that everything makes sense. But at the end of the day, that's elementary, I would say classical physics. It's just the mean energy of a system in a harmonic potential. So it's not that complicated. But now we have a slight problem. I told you before that changing the statistics mathematically is very easy, right? I have an ideal gas, I just replace a plus by a minus or minus by a plus. This is a real system. It's a real gas, so it's going to be interacting. So by changing the statistics using these Feshbach resonances, I'm going to change the interaction energy at the same time. And we need to make sure to separate. I mean, we need to ensure that we are able to separate these contributions, actually. So what you see on the left-hand side is the change in the energy of the trap during this formalization part. So what you see on these greenish dots is what you do when you compress and change the statistics at the same time. So we go from BEC to Fermi as a function of the number of atoms. So there's a nice increase in the energy change. But now let's not go to the change of statistics. We approach it. So if you remember the curve I showed you before, well, I'll just do it. We move down here. If we end up at this point, we change the statistics. However, if we stop shortly before, we still remain in the bosonic part. So we don't change the statistics. And let's see what happens if we do that. So that's what we see down there. So some people call this a Feshbach transition, because it's due to the Feshbach resonance. By comparing these two lines, you realize that the change of energy when you change the statistics is about 4 times larger. So most of the changes, the energy changes that occur during the transition are actually due to the change of statistics and not due to the change of interaction energy. So that's one thing to check. On the right-hand side, it's exactly the same, but now with a temperature which is about 10 times larger. And if you increase the temperature of the gas by a factor 10, you go from Fermi or Bose statistics to Boltzmann statistics. It's a classical statistics, and then you would expect that nothing happens. So we still have the corresponding lines for this Pauli stroke. This is the Feshbach one, and then you would expect to have 0, and indeed, it's very close to 0. The problem is if you increase the temperature, you increase the fluctuations, and then if you want to start measuring things, you get big error bars. But I think it's convincing that this is, what we see here is a non-classical effect, right? Classically, you wouldn't expect anything. So it's a purely quantum phenomenon. That's the main message at this stage. So now let's put everything together. We run the cycle, we measure all the energy changes, work for the expansion compression and exchange of Pauli energy during thermalization and bosonization. And let's evaluate the performance of this engine. First, the work output, which, like as usual, is defined as the work done during expansion, conversion, and compression. And at the same time, we're going to look at the efficiency, which is the work which is produced, divided not by the heat now, because there is no heat exchange, but by the input of Pauli energy, which is due to the change of statistics. So on the left-hand side, we have the work output as a function of the compression ratio, so the difference between the frequency of the tub at the beginning or the end. And we see that it nicely increases. So you get more out by increasing the compression ratio. This is the change that you obtain by going to your normal car engine to a Formula One engine. They have a much higher compression ratio. That's the reason they are slightly faster than your car. And looking at the efficiency, we also find a nice increase. Up to the largest value of reached in the experiment is of the order of 25% efficiency, which is actually not that bad. It's even of the order. So what's the order of the efficiency of a normal car engine? It's of the order of 30%. So it's not that bad. Huh? And what we see also, this violet line, that's what you would obtain in the ideal limit of an ideal gas by just switching the sign, as I told you before. You replace the plus by a minus and the minus by a plus. So that's the upper bound. Let's go back to this difference between change of statistics and just change of interaction. I'm going to compare this Pauli engine and this Feshbach cycle, where we change the size between the distance between two atoms in the molecule, but we don't go that far that we change the statistics. So this is still a little bit of work which is produced. However, if you look at the efficiency, you basically get 0. So if you don't change the statistics, you have a little bit of something and almost nothing. So the effect I'm showing here is basically due or related to a change of the statistics. That's the message on this slide. And then instead of doing just one cycle, you can do 1, 2, 3, 4, 5, 6. You can play and make something useful out of it. And what you see is that, the accumulated work output increases as you would expect. The longer you let your engine run, the more cycles you have, the more work you produce. And the efficiency on the other hand stays constant. So it's a steady engine producing always the same efficiency. You might notice there's a slight difference, or an increasing difference between data and the theoretical prediction is because the system is not ideal. By repeating the cycle, they heat some atoms up and then they leave the trap and then they're gone. And the less working fluid you have, the less work you're able to produce. So that's what we see here. Another important question, what about the energy efficiency of such a device? So you might remember from thermodynamics that as soon as you exchange heat, you have something which is dissipative, or in other words, irreversible. There is no way you can have heat exchange without dissipating entropy. The interesting thing about this Pauli cycle now is this is a Hamiltonian dynamics. It's unitary, if you want to use the word in that context, but actually all the 4 steps of the cycle are non-dissipative. They are Hamiltonian, they are unitary. So there is no intrinsic dissipation mechanism related to that. So all steps are in principle isentropic, the entropy is conserved. And so this engine is free of the usual friction mechanism, which is related to non-adiabatic transitions, if you don't go too far, which are related to the fact that the Hamiltonian doesn't commute with itself at different times. So it could be reversible with a big question mark, in principle. Right? I mean, the experiment is not ideal, so we lose something, we have things that vibrate, so it's not purely reversible, but it could be actually much more energy efficient than a normal heat engine cycle. And let me conclude already. So I told you many things, but actually only 3 points I would like you to remember. The first one is you can actually use quantum statistics as a purely, or generally quantum source of energy. It can be harnessed cyclically by, it converted into work. This is the nice example of this Pauli engine. And all the steps are in principle isentropic. And this might lead to engines that are actually more energy efficient than the ones we have currently. So thank you very much for your attention.
Thank you.
Yeah, thank you. So if I understand correctly, so that your engine transfers the energy from the Fishbach laser to the trap laser or something like that? So that you you put the energy through the Fishbach laser, no?
In a sense,
Yeah, performing the Fishbach resonance.
In
and
a
then
sense, yes.
establish the, say, Fermi degeneracy. And then you transfer this energy by expanding the, say, trap potential.
Yes.
So in a sense that, can I say that your engine transfers the energy from the Fishbach laser to the, say, this trap laser?
if you want to go that step, yes. But that's the only experimental. No, I'm not going to go back, but what I told you before, no, I go back. So what you see here, so to have this BCS-BEC transition, you need to be able to increase or to change the distance between two atoms in the molecule.
That's right.
So there are two ways of doing that, actually. Either you play with the scattering length, and then you apply some external magnetic field, you play this Fleischmann resonance trick, or you make your gas more dilute. And if you dilute it, you decrease the density. So if you look at what people do in semiconductors, when they do this BCS-BEC transition in excitonic systems, they cannot change the interaction. So they simply change the density, and you have the same phenomenon. So you need either to change the A, scattering rate, or you need to change the wave number K, and that's what you do via the density. So there are different ways to change the statistics from one way to the other.
So in the case of the exciton, maybe you can control the chemical potential to change
Chemical
the
potential?
Chemical potential of the exciton, and then they change the density of the exciton, and then this energy goes to...
But it's not just changing chemical potential, you need to change the sign, you change the statistic, right?
Yeah.
You really change the statistic at some point. So it's not just changing, it's not just changing beta or mu, it's you need to change the sign at some point.
Yeah, thanks.
Oh yeah, I have pretty much the same question. I just understand less than Gentaro. So where does the work go, and did you measure the work, or you just computed it from the knowledge over the cycle?
So that's a very good question. So like all the heat engines realized fully in the quantum regime so far, there is no work output mechanism because it's extremely challenging to do that in an experiment. So the work produced was actually calculated, right? So what is determined in the experiment is the energy as these 4 points of the cycle. So this is the next step, how to couple it and to extract it. So where does it go? It actually, the work which is produced is reused to heat the atoms. The fact that we have this deviation here is because we lose many atoms, so the work which is produced by the engine heats the atoms up and they go outside the trap.
So it's basically a heat in the end.
At the end, yes, but like all the heat engines realized in the lab so far, there's not a single one where there's a working heat output mechanism. So you produce it, and at the end you dissipate it again. You have an idle engine. It's like you go home, you let your engine run, you don't move forward, you don't put any gear in it, and you just produce heat.
Excellent. I appreciate your honesty about this.
That's no way. These experiments are not done in 5 minutes, right? Seriously, they're not done in 5 minutes. These are extremely difficult to do, and probably the only promising platform where they can easily couple something to a battery are ion trap systems, right? Because they couple the internal degree of freedom, the spin, to the motional degree of freedom, the phonons. For there, it's there by default. Here, you have to engineer it. You have to put it in. So is this useful at this stage? No, clearly not, right? But it's a proof of principle that it works.
Okay, yeah, very nice. Thank you.
So I have a question about that plot. So do you have a line that, so you said the difference is the loss of atoms?
Yes.
Is that like a quantitative model that shows you that curve?
Yes. So all the solid lines are theoretical simulations of what should happen if you assume that everything is ideal and if you don't lose anything. So all the deviations you see is we lose atoms.
Right. So essentially I'm wondering, like in the systematics of the experiment, so you have a model that puts a line on top of those green dots, which only uses the fact that you're losing atoms. So are you sure that's the only thing that makes this theory fail?
No, we know, we measured. So I didn't show that, but in the experiment, the PhD student measured very carefully at each step the number of atoms, and we know exactly where we lose them. And if you take that into account, it matches. And we also evaluated the amount of energy that you lose by dissipating. You evaporate the atoms, and roughly with the factor maybe 2, the work that is produced is exactly what is lost by evaporating them. So it's consistent, yeah.
Time for more questions.
So very nice talk. So I was just thinking about this. So I guess the easiest part of it to think about as a sort of surprising picture is that it means if you have a gas of fermions, degenerate, and magically they all turn into bosons, then it releases a huge amount of heat.
Sure.
Right.
If you could do it that magically, but I can't.
Yeah. And so we're very lucky that in a metal, the electrons never suddenly all turn into bosons because we would all get burnt. Yeah, okay. So this makes me think of the latent heat of a phase transition in classical thermodynamics. And it just occurred to me, is this something like the upper bound on the maximum possible latent heat that any phase transition can have? Does such an upper bound exist, and could this be it?
Let me emphasize that the BCS-BEC transition is very often called just a crossover to avoid the misleading idea that's actually a phase transition. If you have just S-wave scattering, it's not a phase transition, so it's just a crossover, let's use that word. So in that case, there is no phase transition at all, right? But if if you think about the old Rankine cycle, where he used a phase transition, and if you run that engine across the BEC transition, phase transition, this would be a phase transition. And this would probably be the answer to your question. But here there is no phase transition, it's just a crossover.
I know. No, I was thinking more about not the experiment, but the concept of this thing of suddenly fermions becoming bosons. And is that the biggest latent heat you can possibly have? Is that some upper bound on?
If that's the largest one, it's a very good question. I would naively say yes, because it's very huge, but I don't know. Honestly, I don't know. But it's, could be.
Okay, we should think about it.
Thank you.
Hi, I'm a bit confused by what you said at the very end about everything ultimately being unitary, because to me it seems that you reach this point only if you include your flashback laser somehow in the whole thing, right? Or I don't really understand how you can drive your system with this flashback laser and then say that it's basically a closed system, that there is something that I don't fully understand in this argument.
So the system is isolated. The gas is isolated from its environment. There is no exchange of energy with any heat bath. So there is, we saw many Lindblad master equations in that conference. So this dissipative part is not there. It's a unitary time evolution. It's von Neumann.
But then you have to include the driving laser somehow.
But the driving is
this,
unitary.
right?
You can have unitary driving. I need a hand. If I take my harmonic potential and just change the frequency, this is Schrödinger dynamics.
Sure, but it costs energy, right? I mean,
it costs energy. It's true. I mean, the energy accounting is done, right? So costing energy, so you can have.
Okay, I think so. What you mean is it's unitary, but it's unitary in a time-dependent way.
Unitary, sure, time. Everything is time-dependent. So unitary, I mean, Schrödinger dynamics allow you to change the energy, but the entropy remains constant. That's what I mean.
Okay, yeah.
So Hamiltonian dynamics, unitary dynamics leads to a conservation of the entropy of the system. So in that sense, it's. But I do exchange energy, of course, and this is the energy accounting has been done in the experiment.
Thank you. I think we are coming to the end of this session now. Let's thank both the speakers and